Anna Krawczuk. Anna completed her master's degree in chemistry 2005 and her PhD degree in chemistry 2009 at Jagiellonia University in Krakow. Her thesis was focused on correlation between solid-state optical activity of material and its structural features via the use of experimental electron density analysis. Then she went for the postdoc in the group of Professor Piero Macchi at the University of Bern, Switzerland. And it was at the time when she developed Polar software for calculating distributed atomic polarizabilities and optoelectronic properties of crystalline materials. In 2012, she moved back to the Department of Chemistry at the Jagiellonia University, where she was appointed as a research associate. She was further developing Polar software to create a database of functional groups for fast screening of linear optical properties such as refractive indexes or optical activity. Anna was also an academic teacher at Podhale State College of Applied Sciences. In 2018, she was invited as a visiting researcher to the University of Lorraine in Nancy, France, where she collaborated with Christian Jersch and Benoit Gillot on introducing atomic polarizabilities into polarization energy term. In 2020, she got a call as a junior professor at the George August University in Göttingen, Germany, where she started her own research group. The group follows synthetic routes and adopts advanced theoretical and experimental charge density techniques within the framework of quantum crystallography to get a precise insight into the properties of potentially functional materials. The concept of polarizability database is still within main interest of the group, with more impact on accurate prediction of electro-optic and electrostatic properties of biomolecules. She published more than 50 scientific research papers in peer-reviewed international journals. In 2020, she became a member of the editorial board of Journal of Molecular Structure, and 2022, she was appointed as a vice chair of Quantum Crystallography Special Interest Group, SIG2, of European Crystallographic Association. She's also strongly involved in mentoring young females within the Cyber Mentor STEM program, and active member of Equal Opportunities team at Faculty of Chemistry, George August University. And today, Anna will talk on dipolar group polarizability as a multipurpose tool for predicting molecular and bulk properties. Anna, the screen is yours.
Thank you very much. And I also want to add one thing, that actually Krzysztof was a reviewer of my PhD thesis. So, you know, he already put like the expectations very high. This I must say, but I have to mention that because this was quite an experience. Okay, so, well, first of all, thank you very much for inviting me here. I'm very happy to present you some of the past and current research that we are working on in my research group. And I hope, yeah, okay, the laser is working, so let's continue. So as Paulina already mentioned, the main goal of my group is to find the structure property correlation. We want to understand what is the origin of a property, a molecular property, but also a bulk property. So in principle, we want to simplify, in a way, a prediction of electric and electrostatic properties of mostly biomolecules. But we also want to estimate some linear optical properties, for example, refractive indices. And also very fast, we noticed that there is a quite significant transferability property of the electric moments of functional groups. And we also want to take advantage of that, because this gives us this unique opportunity to go from the atom via a molecule to a bulk property. So, of course, the first question is why polarizability, and in a way why a dipole moment is the main interest of us. Well, if you take a look of a number of properties of materials, it turns out that a lot of them can be directly correlated with the polarizability. For example, you can extract information on a linear susceptibility. Once you have molecular polarizability and volume of a unit cell, this is almost immediately accessible. You can then get information on the electric constant, which also is a quite significant bulk property. And once you diagonalize the dielectric constant tensor and apply square roots on the components, you get information on refractive index. And all of that possible because we are using the polarizability term. But also, if you take a step back and use the dipole moments of functional groups instead of polarizabilities, it turns out that you can also predict electrostatic potential of a molecule, small molecule or bigger molecule. We rely only on atomic dipolar terms to calculate the dipolar electric potential, which we find as a good estimator for the total electric potential of a molecule, in many cases much better than the potential generated by the molecular dipole moment. So those are the main reasons why actually we are excited about those electric moments and still working with them. So as a workflow, one can imagine that, of course, first we have to choose some kind of a building block. Initially, that was a molecule or a set of molecules. Right now, we are focusing more on functional groups. But nonetheless, in all of the cases, we have to have access to electron density distribution, and then we have to have some kind of a partitioning scheme in order to extract information on atomic contributions. So for that reason, we are currently using a Q-time theory introduced by Bader. However, other partitioning schemes could also be applied. So having that in hand, then we are able to partition any property that can be derived from electron density, for example, dipole moment. And then we introduce the dipole moment in such a way that we divide it in two terms. One is coming directly from integration of atomic basin. The other one we call translation component, which defines so-called dipole bond dipole moment. If you define atomic dipole moment in such a way, then getting a polarizability of a single atom is not a problem anymore, because we all know that the dipole moment is nothing else but the change of the dipole moment with respect to electric field. And then we can extract the information on a full tensor of the atomic polarizability, so not only diagonal components, but also off-diagonal components, which means that we fully describe anisotropy of the electron density within a given system. Because it is a second-rank tensor, we can define it in volume units, which on the other hand means that we can also visualize it in a very convenient way as an ellipsoid in the same space as the molecule, so one can extract information on atomic polarizability. Of course, you can sum up to group one and then to the molecular one. Because originally the polarizabilities are really big, when you visualize them, one has to use some kind of a scaling factor to just reduce it a little bit, so all the characteristic features of the property can be visible. So what about those characteristics? Well, first of all, if you just take a general look on those polarizability ellipsoids, one can immediately see that they are usually elongated along the directions where the most polarized bonds are present. So, of course, in most of the cases, those are covalent ones. We are dealing mostly with molecular crystals. But also, what is, I would say, one of the unique things about this approach is that when a very weak interaction is being created, for example, a hydrogen bond, the polarizability ellipsoids are also sensitive on that formation. So if you, for example, compare a polarizability ellipsoid of an atom that is not bonded to a hydrogen bond and when it is, one can see that there is some kind of elongation of the polarizability towards the formation of a hydrogen bond. Very similar thing happens when one has a hydrogen atom. So then we are happy to see that, because then we know that if we introduce a weak interaction into the system, polarizability will follow that route and will express that in the shape and the magnitude of its property. Also, if you take a general look on those drawings, one can see that they also reflect very nicely a symmetry which is present in the system, which means that we do not have to really introduce any additional restraints or constraints considering the symmetry. What is also a quite, I would say, nice outcome of polarizability is that once you have atomic polarizability in hand, you can define bond polarizability. So you can just project a certain portion of the polarizability along a certain bond, and then you actually end up with fully quantitative definition of how electron density polarizes along the bond. This kind of a property has been known already in the literature, but rather in a virtual definition. There was never really given like a very exact one. But in many cases, it is being connected to the softness or hardness of the molecule, which of course then leads to some kind of reactivity correlation. And over the years, we actually studied a number of complexes which allowed us to by observation of which side of a complex is most polarized, allowed us to say what is the most active or side in terms of electrophilic or nucleophilic attack. Recently, we actually started a collaboration with a group from India, of Ranjan Patra, and we got interested in metalloporphyrin scaffolds. They are very attractive building blocks for self-assembly. And we actually did a series of calculations of compounds containing tin and iron. And the porphyrins had phenolate axial ligands. We calculated polarizabilities, we calculated dipole moments, as well as electrostatic potential. And we were very happy to see, to find the correlation between the stability of the metalloporphyrin scaffold and the number of fluorine atoms that are introduced to this porphyrin assembly. So for example, if you take a look on the plots which are given here, especially the middle one, we notice that the more fluorine atoms we are introducing to the system, the smaller the dipole moment gets, which in a way suggests us that the reactivity of the compound can decrease. Very similar information we got from the polarizability behavior and also electrostatic potential. So again, another kind of a brick to the wall, confirming that polarizability may be a very practical tool for reactivity structure correlation. But coming back to the property prediction, this was the original idea standing behind polarizabilities. The idea came out already during my PhD, but then it took a while to actually make it happen. But obviously, one has to test the method. So the first molecule or first crystal that we tested, the method was urea material. I mean, we all know that this is one of the best molecules plus crystal structures to play with when one wants to test the theory for many reasons. A very flat molecule, a lot of possibilities for creating hydrogen bonds, a high symmetry of the molecule itself. Plus, it crystallizes in a very high symmetry tetragonal system, and on top of that, it is a non-optical, non-linear material. So I would say one of the perfect or most perfect molecules one can deal with. So we were very pleased to see that when we compare the refractive indices obtained from experiment with the ones estimated by Polaber, the agreement is, I would say, quite significant. We were a little bit worried that it's so good, so obviously one had to test a little bit more because, you know, nothing can be so good. So we went a little bit further. So for example, here another or molecular crystal, but I would say rather more complicated with lower symmetry, L-histidinium hydrogen oxalate. It is a potential organic NLO material. And we benchmarked our prediction against the experimental values. Those were measured by some of us involved in the manuscript. And also we checked the periodic calculations, which mimic better, I would say, crystal effects. And we were also very happy to see that Polaber predicts those values in a I would say, rather accurate way. Of course, in the meantime, I also started collaboration with Benoit Champagne from University of Namur, and at that time he was using local field theory to predict or to estimate dynamic refractive indices. And he suggested that perhaps we should join the forces and actually modify, let's say, his approach by introducing polarizabilities obtained with our software Polaber. So we joined the forces and we tested the approach on a couple of examples. Here, one of them, again, organic nonlinear optical material. And when one compares the values with the LFT, let's say, corrected with polarizabilities and the experimental values, one can see that the prediction is much better than when the polarizabilities are not being used in the way that is obtained with Polaber. Of course, it's not perfect, but we are much closer to reality than before. The same, let's say, picture is being drawn when one visualizes the dispersion of a refractive index with this modified LFT method, which obviously is like the ultimate goal, because we want to not only see the refractive indices used with static polarizabilities, but actually want to use dynamic ones, because then we have a true relationship with the wavelength. And also, again, if you compare the values of the modified model with the experimental one, in all of the cases, one sees a very nice agreement. Work on that is still ongoing. Hopefully soon we will have also some new results. But of course, in the meantime, when we started using Polaber, we ask ourselves a question, okay, what about those crystal field effects? Because obviously, when we are measuring refractive index of a solid state, directionality is an important issue. Also, the presence of different kinds of interactions is an important issue. So how to actually account for that? With Polaber, we are unable to run boundary condition calculations. We can only build up some kind of a cluster. But then the question is, how many molecules to include? Is 1 enough, 2 enough, 3, and so on and so forth? So for that reason, together with Leonardo dos Santos and Rafael Ligorio, we started a project to combine a kind of an aggregate approach with a dipole interaction model. However, we modified the dipole interaction model in such a way that instead of point dipole approach, we used a functional group approach, and also functional groups were introduced in terms of polarizability, which was then used to correct the dipole moment and the polarizability of a central molecule. So we wanted to know if it's sufficient to mimic the crystal effects, and also if it's possible to somehow correct for example, refractive index behavior. So obviously we had to compare, let's say, our modified model with something more established. So we used, let's say, a quantum calculation, so exactly as it was introduced at the beginning, and then this ADIM model, so the modified model. So we were very happy to see that in all of the examples we took under consideration, the agreement between the modified model and let's say regular one was quite good. However, if you take a look here on the picture, the quantum model had some troubles with reproducing or with calculating some of the atomic polarizabilities. For example, in some cases like this carbon atom or here hydrogen atom, we were getting a negative values of polarizability. This is obviously physically impossible, so we started to take a look what's going on, and we noticed that if we deal with two big clusters, and then we have some troubles with integrating the electron density with the partitioning scheme that we are using, then the definition of those of the zero flux surfaces is maybe sometimes ill, leading to the negative values of polarizabilities. But if you then correct this model with this modified dipole interacting one, and I hope that the animation works. This is those green ellipsoids, so one can see that we can actually correct for those meaningless negative values of polarizability and reproduce in a very nice manner the behavior of the polarizability, apart from the ones which were already there. Also, when one looks at the values of refractive indices, one could also see that if you include the most crucial interactions of the system, for example, the strongest hydrogen bonds, which means including two additional molecules, the prediction, at least of the overall refractive index, becomes quite accurate. There is no need to go higher with the number of molecules. That, of course, gave us an idea that there is no need to launch a very sophisticated with a huge system calculations. It is enough to only account for the most important weak electrostatic interactions. But also, in the meantime, we noticed a super important feature of a polarizability, which actually launched a very long-term project on a database for polarizabilities, and this is transferability. Well, very fast we noticed that atomic polarizability is too sensitive on the changes of the chemical environment. But on the other hand, we noticed that if we sum them up into functional group, the functional group holds very well when changing from one system to another. That immediately, of course, gave us an idea, okay, building block approach, and perhaps developing a tool which will allow us this fast screening of optoelectronic properties. And the project was launched in 2019 together with my colleagues. So we started, of course, with atomic polarizability tensors of some chosen rather randomly molecules. We defined, of course, a functional group via hybridization, a first neighbor, as well as the chemical environment. We then, of course, ended up with the functional group polarizabilities. Since it is a database approach, then obviously one has to also define a local coordinate system. And then would be nice to apply some kind of a clustering to have the best representative of the polarizability within a certain family. Of course, one could take also the averaged value, but our experience showed that clustering is more accurate. And then, of course, the database is ready and can be at least initially launched for optoelectronic properties. So for clustering, we use the genetic algorithm because it seemed to be most natural, especially that it is actually observed daily in the nature. And we were benchmarking our results against the polarizability obtained straight from the QTAME distributed polarizabilities, and also against the refractive index if that information was available at that time. So we were very pleased to see that the deviation, so the average deviation was very low. So if we use the clustering mode, it was around 1.5%. Even if the clustering was not used, just average value was taken into account, also the values were quite low. When it comes for the physical properties such as refractive index or the electric constant, the agreement was also pretty impressive. So it gave us the let's say the urge to work further on the database. Currently, especially Piero is working on making some rather more automatic way to define the functional groups. However, my group, we, apart from this data approach, we decided to actually turn a little bit and actually focus on biomolecular assemblies, in particular to predict dipole moments and electrostatic potential. So we became quite obsessed, especially me and Rafael, and result is a database which finally has a name. I mean, it's not a very sophisticated one, but it works. It's called Groupol. And to define the database, we of course had to first define a functional group. So for that reason, we chose prototypes. Those were 25, not too big, but not too small peptides. From each of them, we could extract around 5 to 6 functional groups. And then we engage force field calculations in order to generate and consider different conformations of those peptides to account for different kind of chemical environment. Those calculations were done with charm, and once this was done, then we went to quantum calculation. So we had to partition electron density, calculate atomic polarizabilities and dipole moments, and then of course extract the group property. As a database entries, again, local coordinate system had to be defined. We use inertia tensor approach, which seems to be the most straightforward one. And because the idea was to predict properties of interest of bio people, then we also decided to create as an input file something which is very familiar to bio people, and this was a PDB format, and everything is presented in such a way. So of course the first question is, does it work? How to check it? Very easy. You calculate polarizabilities and dipole moments and electrostatic potentials for a molecule. You extract information from this one and to the database, and then you take the values from the database and you try to reproduce the same thing again. So here just one of the many examples. If you compare the numerical values between like the exact values from quantum calculations and the ones from the database, I would say the agreement is quite impressive. Something that one can think, okay, we can work further on those results. What about dipole moments? Well, we define those group dipole moments. So of course, we are not only interested in the magnitude of the property, but also the direction. Because, you know, in many cases, although we are able to predict the magnitude of an effect, the direction is completely off. So I always prefer to see first the correct direction and then to correct for magnitude than the other way around. So if you compare the dipole moment vectors, one can also see that the database approach works pretty well with comparison to the quantum calculation. One can also always observe a so-called anisotropy of polarizability, which is defined here within the equation. Of course, the results are a little bit more off, but still we see a trend of the behavior of the anisotropy in a correct way. So what about the electrostatic potential? Well, this was our first result. I mean, I'm showing small examples, but just to show you the mistakes we did in the meantime. So at the first glance, everything seems fine, but then when you start looking more closely, you see, oh, this is really wrong, right? I mean, the most negative part on the carboxylic group is not where it's supposed to be. It's completely in the middle between the atoms. And then we were like, yeah, of course, this is obvious, because by averaging the atomic contributions into a group property, we sum up the vectors on individual atoms, and then the resulting orientation neglects, let's say, this natural behavior of an individual atom in the functional group. For most of the functional groups, this is not such a problem, but the ones where they have this natural directionality, as for example, carboxylic group, this is quite a crucial thing. And one then has to take a step back and correct for this effect. So we used a very easy model. We call it a split model. So we just say, okay, in those groups where we know that the directionality is present, instead of taking a group dipole moments, take those atomic ones and then model electrostatic potential based on that. And once this is done, then if you compare the electrostatic potential with the exact calculated one, then we end up with something that is reliable, and we are satisfied with that. This is just a different representation of the electrostatic potential, but if you compare especially this part, all is very nicely reproduced. So what next? Now let's go crazy, because now it seems it works for smaller units. Let's go crazy with bigger units. So we did. So our first approach was actually to model insulin chain A. So we were able to reproduce correctly the direction and the magnitude of the dipole moment, at least with the data that was already reported in the literature, atomic and group polarizabilities as well, and of course a beautiful reproduction of the electrostatic potential, which I would say it's a honey to my heart. But then of course the appetite grows while eating. So another thing we want to see, can we actually account for solvent effects and perhaps some kind of a pH dependence? So what we did, we used the explicit solvent model. However, all the water molecules that we placed around the protein were represented in terms of group polarizabilities. And normally when you use boundary conditions or some kind of dynamical simulation, you build up a supercell, right, a box with water. In our case, we don't have this privilege, so we had to deal with it somehow. So instead of introducing a box, we introduced an ellipsoid shape around the protein to account correctly for anisotropy. We also use this dipole interacting model to correct dipole moments and polarizabilities of the protein. And then we also try to use some kind of modeling of PhD dependence. So just to show you how it looks like, so if one normally would have this box, but in our case, we do not use the box, but we are using this kind of an ellipsoid, which one can define. And this is actually an interface, a graphical interface of Drupal. And then once this ellipsoid is being drawn, one can take into account the solvent effects. In our case, of course, it is water. So what about this pH dependence? So to have this information in hand, one has to assign charges to each group based on pKa values. We then somehow generate a charge dipole moment, and then the atomic dipole moment or core dipole moment, which we already have in hand from, let's say, regular calculation, is then corrected by this charge one. And we can then observe the change of the electric moments with respect to pH. So our tests were done on myoglobins. For main reason was that actually there was experimental data available for the dipole moments with respect to pH. And believe me, that was a huge surprise for us that we have a fantastic agreement between the Drupal prediction of the change of with respect to pH to what was actually reported as experimental values. We are now, of course, working on more examples, but this already gave us a lot of hope that we are not only able to account for solvent effects, but we are also able to mimic a pH dependence of a system. One last thing is a hydrogen bond formation, because of course when you look at the protein, one has to remember, oh, come on, there must be some kind of other interaction involved. So if you, for example, look at this place, one can see that the molecule moves, and at some point it will create a hydrogen bond. This usually applies for terminal groups as well as peptide bond, and obviously the direction of the hydrogen bond will change the secondary structure of the protein, which means that it will change the optoelectronic properties. So what one has to do, one has to account for that. So we did here only an example on the peptide bond. So we did account for that. So we are now screening the whole system, looking at the angle between the donor hydrogen and acceptor. Those angles are the most crucial ones when one wants to distinguish between secondary structures of proteins. We fixed the maximum value between the hydrogen atom and acceptor to 2.5. Our experience shows that this is enough to account for all the possible interactions. And then, of course, we started to look what kind of angles we are ending up and what they are actually telling. So in principle, if you end up somewhere with 90 and 120 degrees below, then there is an indication of parallel arrangement, which suggests a beta sheet formation. Angles which are higher than 130 degrees point more towards the alpha helix formation. And when this angle is at around 120 degrees, then usually we observe a formation of two hydrogen bonds at the same time. So then, of course, one has to check how the dipole moments and polarizabilities behave in such a system, depending on the angle. And if you take a look on the graphical representation here, it is very much clear that we should take into account the hydrogen bond formation, because the dipole moment as well as polarizability, they make quite significantly change with respect to that. Once this is taken into account, then you can again model electrostatic potential, and the electrostatic potential will express a potential formation of a hydrogen bond for a system at that certain time. And at the end, as a summary, I would actually like to show you what is the perspective of our approach, what we would like to improve. So obviously, first of all, one has to include more functional groups, and this is mostly prosthetic groups if we talk about the biomolecular assemblies. We want to include metal ions because those are the most common assemblies in proteins. As I mentioned before, this automatic identification of functional group would be super beneficial, and now Piero and his group are working on that. Something which I am thinking about since many years is to use a different partitioning scheme of electron density, but there's never time to actually start the project. So if anyone has a will to do this, please write me or call me. I will be more than happy to actually start such a project, because I know that there is a potential behind other partitioning schemes. It's just, not enough hands and heads to work on that. The other thing is, if you focus on physical property prediction, then obviously including dynamic polarizability, so frequency dependence would be a huge step forward to make the database more reliable. And something which I would say is quite ambitious, and I'm not really sure that it's possible to do, but since we have a very precise definition of atomic polarizabilities and group polarizabilities of a system, one could think that they could be included in some modern force field calculations. But this is, of course, a little bit of a problem, because this is not the only parameter that has to be included, so one would have to think how to actually adjust this to make a nice picture. And of course, at the end, I have to acknowledge some of the people that were involved in my project. I call them three musketeers. I hope that they are not offended by that. And this is Piero, Leonardo, and Raphael. So with Piero, I started my journey on polarizabilities. Leonardo then joined the forces, and we are still collaborating quite actively. Raphael is currently doing PhD with me, and he's absolutely a mastermind standing behind the biomolecular work. This is Raphael here at the back. Then also there were many women on the way, young women who were very motivated, and also Benoit, who was also supporting our project. If there is anyone I did not mention, I apologize, but I am super grateful for all the support over the years. And with that, I would like to thank you for your attention, and I'm open for discussion if there's any. Thank you.
Thank you, Anna, for this excellent talk, which is now open for questions and comments.
Yes.
And so please write your questions into chat. And
before we have any question in the chat, I have plenty of questions.
Now I am afraid.
You actually started it because I wanted to ask you about how these polarizabilities depend on the atomic partitioning scheme and how the transferability of polarizabilities depends on the scheme you are using too.
I mean, I am absolutely sure that there is a strong dependence on the partitioning scheme. So some time ago, I think Piero did some kind of test. He used, I think, Hirschfeld partitioning also to obtain estimation of atomic polarizabilities, and they looked quite different. So usually, for example, hydrogen atoms, the ellipsoid is much bigger than it is when you use the Bader's partitioning scheme. But on the other hand, it seems to me that the Hirschfeld partitioning may be more chemically intuitive, because we somehow think about electron density as overlapping. Bader's theory does not allow for overlapping of electron density of interacting atoms. Hirschfeld partitioning, yes. So I would think that the picture would be very much different. About the transferability, I am unable to say, but I think it would be anyway kept. However, just a little bit different information would be extracted at the end of the day.
I can comment on this as well. So there was a lot of work in my field on ways of partitioning density and polarizabilities, and basically nobody uses Bader methods. The reason is that Bader methods have those very weird shapes of atoms, which we have shown on one of the pictures. And if you are interested only in dipoles and dipolar polarizabilities, that's not such a big problem. But if you want to go higher to quadrupolar and so on, the problem is that this method converges really terribly. So we made a comparison when we used another scheme of partitioning, actually basis set based. It doesn't matter what it was, But the point is that we compared with people who used those Bader basins, and we were obtaining very good convergence of things like dispersion energies, polarization energies for pretty big molecules, taking only partitioned dipole and quadrupole properties. And the other work, which was really very similar, except for using different partition, had to go to L equals 7. So we used only L equal 1 and 2. They went to L equals 7, which basically makes this method not practical at all. Nobody wants to go to L equals 7 for any bigger molecules.
Yeah, I mean, as you said, since we are focused mostly on dipole moments and polarizabilities, I absolutely understand that this is not a problem with Bader's theory. However, also, if you want to partition bigger system, it becomes a problem as well, because it just does not deal well with bigger systems. So that's why also the database approach to somehow avoid dealing with calculations of such big systems.
Actually, Hirschfeld method is kind of most popular. Most people in my field use Hirschfeld. There are improved, better methods. It's called Stockholder method and iterative Stockholder, which seems to be the working best now, but still people use Hirschfeld because it's so trivially simple.
I am absolutely fully aware of that. I mean, I already discussed that with Alessandro Genoni, that perhaps we should finally join the forces and actually go towards Hirschfeld partitioning. But as I said, there's never enough time for me.
You showed examples for different kind of polar molecules, but altogether they were neutral, right? How it works with
well, not
charged
really,
molecules?
because when you had we also deal with charged molecules. So, for example, with the proteins, we are dealing with, we are charging them, let's say, artificially also to account for that. Yes, also when you look at the PhD difference, no, you start with isoelectric point, but then you are shifting to somehow artificially also charge it. So we are also accounting for the charge in the system.
But when you build your data bank, your model molecules are only neutral, or?
I mean, if you take a look on the functional group, they are also charged because, for example, if you use a Twitter ionic form, then obviously the amine group is protonated and the carboxyl group is deprotonated. So in a way, we are also accounting for that.
Mm-hmm. The potential you are predicting, you plotted it on the surface, right?
Yes.
And you had only one slide showing the entire potential.
Yeah, I mean, there is not that much time to show more examples.
Yeah, but that's that somehow reminded me, because this is so you compared it to a potential computed from point charges, because you had like negative values of potential nuclei position. So it's not like the potential you would directly get from electron density, right?
No, we were for smaller systems, we were calculating the exact electrostatic potential. I don't know, with the use, for example, of Gaussian software. But when we were switching to bigger systems, then we were only using the database approach to reconstruct the electrostatic potential. So for the big proteins, we had nothing to compare with, really.
Mm-hmm. Yeah, but maybe I misunderstood the picture you have shown. But anyway, when you predict the potential, you have you ever evaluated the potential, like the entire grid of the potential from your method and from the quantum calculations, or you just focus on the isodensity surfaces or the global properties like dipole moments, etc.?
I mean, we were also trying to, let's say, to modify the distances, because we know that at a certain point we have this polarization catastrophe that, for example, polarizabilities just explode. Yes. But for this particular reason, we are actually using a damping factor to prevent that. So we are using the toll damping approach. And then I would say it holds still pretty well. So we are aware of that fact. We are aware. But anyway,
Okay,
I mean, no one usually goes really lower than the van der Waals distances, so it's not always such a problem, I would say.
If you would like to apply it for electron diffraction, then you have to have everything correct, not only the van der Waals.
This is maybe the next step for the future. There's some baby steps, you know, baby steps.
From my perspective, is different now.
I am fully aware of that.
I also could have a question, and if you reconstruct the electrostatic potential for a series of similar systems, as Pulitzer did a long time ago, getting nice correlations between different parameters of describing electrostatic potential, then are you able to get similar correlation between some bulk properties and parameters of such reconstructed electrostatic potential using your Drupal data bank?
I mean, right now, not yet. Right now, we were focusing on reconstructing the electrostatic potential in a correct way. So that was the first idea. I mean, of course, if we are able to reconstruct the electrostatic potential, that means that we are also able to reconstruct a polarizability of a system. And based on this property, we can then correlate with a bulk property, but not yet with electrostatic potential. So that's something to consider, definitely.
So you focus especially on hydrogen bonds as an example of intermolecular interactions, right? Or weak interactions. Have you looked on halogen bonds? Do they also somehow modify the potential, or some other kind of?
I mean, with proteins, not yet. Again, baby steps. With smaller systems, yes. For example, I was showing you this studies we have with a group of Ranjan on metalloporphyrins, and yes, we definitely observe quite significant changes in dipole moments, in electrostatic potential, and polarizabilities depending on the level of substitution within the ligands. So we see a very nice correlation there as well. We now would like to also study, let's say, dimers where halogen bonding is more pronounced. So far, not yet results. Maybe next time I can then tell some more.
In the case of proteins, what kind of resolution of macromolecular protein data is needed in order to get, say, reasonable outcome? I mean, would you get something useful if you have protein data above 1 angstrom resolution?
I mean, but we do not need really a protein data. We only we need atomic coordinates. That is true. Actually, no one I think tested that yet of us. How this is dependent on the resolution. But true, that should be also somehow considered. But I mean, we chose the examples where we had let's say good experimental data because one wants to start from a good point. But also we had experimental data of the properties, so this was even more important. And also we were starting with the proteins without any add-ons. First of all, this was a very clear protein, only amino acid residues, because that was the original way how the data bank was being produced. But yeah, this is something that we should definitely take a look on, that how much that depends on the resolution. True.
Very challenging question. Would this work for electron diffraction protein data?
Yeah, this we have to check. I mean, I understand why Paulina is asking the questions about how reliable is the electrostatic potential. We have to check that. I have to, Rafael, I think, is listening, so I'm sure that he's already taking notes.
Mm-hmm. Yeah, as we do not see questions from the audience to you, thank you, Anna, for this really great lecture.